So we've seen an example of a vector field that is not conservative, and we'll see a little bit more, exactly why that vector field is not conservative in the remainder of this lecture, once we get to defining what's called the curl of a vector field. But let's do an example of a vector field which is, in fact, conservative. And this is a very, very strong example, because it's coming directly from physics, and it describes a number of different situations in various physics. And this is what's called an inverse square law. And specifically, this is a type of law where the intensity of some quantity is proportional. This is typically the symbol used for proportional to 1 over the distance squared. And very often, an inverse square law in physics is what's called an inverse square force law, because where this typically comes up, and the first time you'll see this, is for forces between in two main scenarios in physics. The first is with a Newtonian gravitational potential. So a Newtonian gravitational force between two masses. A little bit later on, we'll use capital M for one mass and lowercase m for another mass. And another time we see the inverse square force law is with the electrostatic force. Between two charges, which we can call capital Q and lowercase q. This is really a great example of a conservative vector field, because the force field in either of these two cases is actually coming from the gradient of a scalar potential function. And because both of these are essentially described by the same mathematics, we'll just call that scalar potential function phi, where this scalar potential function is equal to some constant c divided by the distance between the two objects squared. R is the position vector with at the base. Its base is at, the potential is just the c over the distance squared between those two objects. So in the example of the gravitational force, if this is mass m and this is mass m, small lowercase m, then r, the displacement vector between m and m, is just this r right here. In the same exact picture for the electrostatic force. But this coefficient c, this constant c right here, changes depending on whether we're dealing with the electrostatic case or the gravitational case. But in either cases, this is the correct form or the potential energy and specifically we're going to show right now why this potential generates an inverse square law for the force. So the gravitational force, or the electrostatic force, between two objects is the gradient of this potential phi, and that's equal to the x partial derivative of phi, the y partial derivative of phi, this should be x, and the z partial derivative of phi. And it's convenient always to write the gradient vector of a function as, in this case, a 1 by 3 vector, but depending on what dimension you're in, it's going to be a 1 by whatever your dimension is vector, so as a row vector. And so to evaluate this gradient, we have to go through and figure out exactly what each one of these partial derivatives is. Remember that 1 over the length of r, and we're putting our coordinate system at the location of one of these masses, mass m. So 1 over r will just be, in Cartesian coordinates, 1 over the square root of x squared plus y squared plus z squared. And therefore, when we go through and take, we'll just do one of these partial derivatives, call it d phi dx, will be equal to the x partial derivative of c times x squared plus y squared plus z squared to the negative 1/2 and therefore by the power rule and the chain rule, this is going to be equal to c times negative 1/2 times x squared plus y squared plus z squared to the negative 3/2 times 2x, or d phi dx is equal to negative, we'll say c times negative x over the square root of x squared plus y squared plus z squared cubed, which is just negative c times x over the length of r cubed. And this is going to be exactly the same for the y partial derivative and the z partial derivative, only we'll have a replacement of y for the y derivative and z for the z derivative. So this is going to be equal to then negative c x over the length of r cubed negative c times y over the length of r cubed negative c times z over the length of r cubed, which can be simplified and rewritten as follows. And we're going to factor out some things here. We're going to factor out the c from the vector, negative from the vector, because each component has a -1. And we could factor out length of r cubed, but instead of doing that, I'm just going to factor out the length of r squared, and we'll see why in 1 second. This becomes negative c over the length of r squared times the vector x over length of r, y over the length of r, and z over the length of r. And you hopefully will see why we've written it like this, because this now says that the force is equal to negative c over the length of r squared, and this vector right here is a unit vector that points in the direction of the mass, in the mass example of the mass m, but in the charge example, if you repeat this picture but with charge capital Q and lowercase q, this vector is a vector r hat that points in the direction from the base vector, or the base object, to the other object. This is exactly r hat. And this gives us exactly what we were talking about before, in that it's telling us that the force for either of these two cases is exactly this vector right here. So depending on what the sign of c is and the value of c is, that's going to directly determine the direction of this vector. However, we do have exactly that if we take the magnitude of this vector right here, the magnitude of r, or the magnitude of the force vector, if you go through and calculate this, well, the magnitude of this vector right here is going to be the absolute value of c, whatever that is, over the length of r squared. And so this gives us exactly what we started out looking for, which is that if we look to the magnitude of the force vector F, this is going to be exactly equal to the magnitude of this, which sure enough ends up simplifying to the absolute value of c divided by the length of r squared. You go through and calculate this magnitude, and this gives us exactly what we want. This is saying that the magnitude of force is directly proportional to 1 over the distance squared between the two objects. And this is a very neat example. If we go through and kind of look at what c is in each individual case, you can go through and kind of determine exactly what that's going to be in the gravitational case. You're hopefully familiar with c being equal to the gravitational constant, it's called, times m, so g times m times m, which will give you exactly the force law. The force is equal to, or magnitude of force is equal to g m over length of r squared. And sure enough, in terms of the direction that this is force, this is pointing, well, we know that c, the masses will always be positive, so c will be positive because g is a positive constant. And what this means is if this is mass m and this is mass m, then the force vector will be pointing negative in the direction of negative r hat, so in this direction right here. In the electrostatic case, it's a little bit more complicated, but it's not that much more complicated. The electrostatic case, C is equal to negative electrostatic constant times charge 1 times charge 2, and electrostatic constant is positive, charge 1 and charge 2 could both be either negative or positive, in which case we have different scenarios, right? If charge Q, the charge 1 we'll say is negative, and charge 2 is negative, or if charge 1 is positive and charge 2 is positive, this gives us that C itself is negative. And if C is negative, this is going to be good because this negative sign cancels this negative sign. And this is good because when we go through and look at a picture, say, of the forces, of the actual force vector between Q and Q, this force vector, C, is negative, the negatives cancel out, and the force vector is going to point away, which we expect if the charges have the same sign. However, in the opposite case, where the signs do not match, we have that C is positive. If the sign of Q and Q are not equal, C becomes a positive constant. And we have the reverse scenario where the charges are being attracted to one another. Right, so there are many other areas where inverse square laws show up in physics, but this is a great example of showing a conservative force field, because it's coming directly from a very physical example. And not only that, we can actually go through and visualize this in the following way. So if we visualize this force field and actually go through and plug in what this force field is going to be, it's going to look like the following. And this is, you can see a plot here of this force field, this gradient vector field for this potential, where you can clearly see at any given point, if you move lowercase q, that charge around any given point, this vector field is giving you the force that you would experience at that point if q is located anywhere around this. And this is specifically for both charges being equal to one another. Obviously, the magnitudes and the values of this will change as C changes if the charges or the masses are different values. But this is just if for everything normalized to 1. So the next thing that we want to talk about is the topic of differentiation of a vector field and what it means to differentiate a vector field. And we mentioned before that this is a vector field is an object that is much more complicated than a scalar field. And the reason for this is for two main reasons, twofold. A vector field has both a magnitude and a direction, associated with every point. So because of this, actually defining the rate of change in a certain direction of this vector field is a little bit more complicated. We have to be a little bit more careful with how we do that. Whereas a scalar field, we can just use the gradient of that scalar field. A vector field, on the other hand, we have to be much more careful with how we define the rate of change. And it turns out that we actually have two main different rates of change that we can define for this vector field. In general, these different types of rates of change will give us a full picture for a given vector field about how it's changing. But these two types of rates of change are called the divergence and the curl of the vector field, respectively. And in some sense, the divergence gives you the amount of stretching or compressing a vector field is doing. And the curl of the vector field, so I'll do kind of summarize this here. Two main types, or main ways of measuring the local rate of change, or say local change in a vector field. The first one is the divergence of the vector field F. And to describe this in words would be to say that this is a scalar function which measures the total compression, and we'll say not total or net compression or expansion of F, vector field F, at every point. That's the divergence. And the curl of a vector field F, also sometimes called the rote of the vector field F, to denote rotation, is a vector field. So it's a new vector field. Remember, a scalar function is the same thing as a scalar field. So the curl of a vector field F is a new vector field which measures the total local rotation, or the net rotation of the vector field F at every point. And so these are the two things that we typically use to measure the rate of change of a vector field, and will give us a lot of insight into the changing of a vector field. So we'll start by defining the divergence and then move on to defining the curl of a vector field F. So to define the divergence, what we'll do is consider this picture right here. So first assume that what we're going to do is we're going to go through and give some motivation for why the divergence is defined the way that it is. And in order to do that, it'll be very convenient to apply some physical language here and actually consider a very physical example. So in this this motivation, you think of this as motivation for defining the divergence, and eventually we will define it as we move throughout this motivation example. But throughout this example, what we'll be thinking of is the velocity field for a fluid flow. Right. So let's say we have some sort of vector field that gives us a velocity field. So we'll say that we have a velocity vector field we'll call this for short V, where this vector V is a vector of three functions, right, of vector in 3D, so a vector field in 3D. Each one of these, V1, V2, and V3, are functions of position in space and possibly time as well. But so we have a velocity vector field, and what we'll consider is we'll consider the flow of mass through this field V. So specifically to do this, we'll consider what's called the behavior of the mass density function, rho of RT, where rho of RT is the mass density function at any given point R, so any given point in three-dimensional space, and also in time as well, because if the mass is flowing with respect to time, this is changing with respect to time. Just a quick thing that we want to point out here. Remember that velocity has units of length over time, and the mass density function, because we're in 3D, will have units of mass over volume or length cubed. And that'll be important to kind of think about when we're going through and doing these calculations here. So the next thing that we're going to do is we're going to consider an arbitrary point in this vector field, immersed in this vector field. And what we'll be considering is the flow of mass through a very small cube surrounding that point, or a very small rectangle. It doesn't necessarily have to be a cube. I've drawn a cube here, but each one of these things could be different. Delta x, delta y, and delta z could be different. The main idea is that we're assuming they're very small. So delta x, delta y, and delta z are all much less than 1. And what we want to do is get an idea of how to express conservation of mass inside this small cube. Right, so it's definitely helpful now to kind of maybe move over to two different vector fields, possible velocity fields, that we're going to kind of consider, and get kind of a nicer picture of this. So this cube here is immersed in some fluid flow field. So if we'll move back to that other example that we just talked about, just because I have the plot up, and we'll kind of look at what this picture looks like. So this is a picture here of the scenario that we're talking about, where we have some sort of small cube immersed in some vector field, and we're considering the flow of mass, right, through this cube. And what we want to do is try to express the conservation of mass in this cube. We're trying to do what's called a mass balance in this cube. In engineering class, you would call it a mass balance. But really, this idea is very fundamental to the differential, the derivation of both the idea of divergence, and also to we're going to derive what's called the continuity equation in the next couple pages. So the whole idea here is that this cube is very, very small, right? We're going to kind of go very, very small with the cube, as small as you could consider, right? And that's going to make certain approximations valid, and then we'll take the limit as that cube goes to zero. The size of the cube goes to zero. Right, so the idea here is that we have a very small cube. This is kind of a picture of a cube in this vector field with a side length value of 1, but we're talking a very, very small cube relative to the vector field in order to get kind of a good approximation of the vector field and not much changing of the vector field throughout the cube. Right, so even if I try and zoom in here, this is an h value of 0.007. It's very small. I'm going to make it a little bit bigger just to kind of show the picture here. But the idea is that we're taking the limit as eventually as this goes to 0. This cube gets really small. But so we'll consider the cube and the flow of the vector field through this cube. Another good example. This is, remember, this example right here. For the gravitational field, this is what this vector field is. But you could consider this idea with any vector field that you can think of, as long as it's smooth, or its component functions are smooth enough in the region that you're evaluating it. This vector field right here is a vector field that is, in some sense, rotating around the unit circle in the xy plane. So all of the vectors are sort of rotating around that unit circle, which maybe could be characteristic of a magnetic field. If you think of the way that a magnetic field behaves, maybe around a coil, so a single line of or circle of current. If you have a wire in the xy plane, the magnetic field is going to sort of behave like this. And we're still kind of, even for this vector field and any more complicated vector field, we're thinking with the same idea. We take a very small cube. It's a very, very small cube, and we want to consider the flow, right, of mass in our example now through this cube. But we'll see that the continuity equation can actually be used to express conservation of any quantities that are conserved, which is very cool. So back to our example here with the flow of mass through this vector field V, this velocity vector field. And what we want to do is first find an approximation to the total mass entering one side of the cube, one specific face. And what I'll do is I'll label each one of these points. This point we'll call A, this point we'll call B, this point we'll call C, this point we'll call D, and this point we'll call E, this point we'll call F, this point we'll call G, and this point we'll call H. So this is I've drawn a very big cube, but remember this is a very zoomed in picture here. This cube is in reality a very, very small cube. And because it's so small, as long as the vector field is smooth enough, right? It's smooth enough around this point. As we get smaller and smaller with the cube, we can actually get a nice approximation. Specifically, we'll start with the total mass entering the cube at face EFGH per unit time. And this is approximately equal to what? Well, let's try and get in a nice approximation here. EFGH is the back face of this cube. And the total mass entering is going to be exactly or approximately equal to, when delta x, delta y, and delta z are very small, the density times the y component of velocity evaluated at some point. Because this is so small, we'll just choose the back face of the cube right here. So the cube has a front face midpoint here, and then a back midpoint here. We'll choose to evaluate it here at this back midpoint, the velocity here. Because the cube is so small, essentially the total mass entering at EFGH per unit time is going to be the density times the velocity at this midpoint right here. So this is exactly the point. X, y plus delta y over 2, z. Times the area of this face, which is delta y, or delta x times delta z. So we have an expression for the total amount of mass entering at this back face. We want to get an idea of the total amount of mass leaving the front face, so leaving A, B, C, D at this point right here. This is, again, per unit time. And this is going to be approximately equal to rho V2 at, so this value, the total amount of mass entering, plus the change with respect to y in this rho V2. And this is all times delta x, delta z. Right, and simply put here, right, this is just because of, we know that the change in rho V2 over the interval delta y, right, is going to be exactly, if you have, say, a plus b minus a, this is equal to b. This is kind of the idea here, right? If you have an expression for the change in y over the interval delta y, that's what this delta y of this means, or delta sub y of this means here. This value is exactly the correct value at this face. So notice I haven't used an evaluation here at this point. We're going to use what we know about multivariable calculus to get an idea. in a nice simplification here. And you'll see why in 1 second. Remember, from multivariable calculus, the concept of linearization or approximation, it's almost the same thing as linearization or approximation in 1D calculus, but say in multivariable calculus, if you have a function of x and y, the change in that function is approximately equal to the derivative of that function. In this case, you'll see the x change in that function is the x partial derivative of that function times the change in x for small values of delta x. And similarly, the change with respect to y of that function is approximately equal to the y partial derivative of that function times delta y. This is for a function of two variables, but this applies equally well to functions of any number of variables. And thus this expression right here is going to be the same thing as, or approximately equal to, rho v2 at the point x, y plus delta y over 2, and now plus, it'll be the y partial derivative of rho v2 at this same point times delta y. All of this times delta x, delta z. Alright, so this is the correct form for writing this, because we're going to see that what we're trying to do is motivate the definition of the divergence the way that we have it. So this is a correct approximation for the total mass leaving ABCD per unit time. This is the correct approximation for the total mass entering EFGH per unit time. And it's definitely important for me to point out why this works. And the idea to think about here is always, the units. What are the units of this expression? Well, we know that rho has units of density, which is mass per volume, or length cubed. The velocity v2 has units of length per time. And then here delta x, delta z, each one of these has units of length. So the ultimate units of each one of these quantities is mass per unit time, which is a nice little kind of like check to make sure that we're kind of going in the right direction here, the correct direction. So the idea here is, well, if this is the total mass entering through this back face, and this is the total mass leaving through this front face, an approximation to the net change in mass per unit time along y is going to be approximately equal to the subtraction of this quantity and this quantity, or this minus this. And if we copy this down, it's a little bit long. You can kind of take all this and this right here and copy it down and subtract them if you want, but you're going to see that this first term gets canceled out here when you subtract the total mass entering from the total mass leaving. So the net change in mass, and this should say also along y here. Along y per unit time is approximately equal to, when we do the subtraction, the y partial derivative of rho times v2 evaluated at the point x, y plus delta y over 2 z times delta x, delta y, delta z. And this is special for a number of different reasons. One of the big reasons here is that it's a relatively simple expression involving the partial derivative. And the other reason that it's special is that you can do the exact same thing here along x and along z, and not much is going to change except for the components. The net change in mass along x per unit time is going to be the x partial derivative of rho times v1, where v1 is the x velocity component, and this is going to be at the point x plus delta x over 2 yz times delta x, delta y, and delta z. And you have a similar equation for z. The net change in mass along z per unit time will be the z partial derivative of the density times v3, and it becomes then evaluated at the point x comma y comma z plus delta z over 2. And what this means then is that the total net change in mass in this rectangular prism, right, in this shape, is going to be the sum of these three quantities. So the total net change in mass this is, remember, through the boundary. This is also per unit time. Is going to be the following. It's the sum of these three quantities. So the total net change in mass through the boundary per unit time is going to be the x partial derivative here. And we do have a little bit of a simplification because each one of these has a delta x, delta y, delta z in it. We can just add all these up and bring the delta x, delta y, delta z over and factor it out. The net change in mass through the boundary of this rectangular prism is going to be the x partial derivative of rho v1 plus the y partial derivative of rho v2 on that back face. And then lastly, plus the z partial derivative of rho v3. all of this needs to be multiplied through by the total volume of the domain itself, delta x, delta y, delta z. But this is the correct approximation to the total net change in mass per unit time through the boundary, right, of this region right here. And this approximation gets better and better and better the smaller delta x, delta y, and delta z are. And the next thing that we need to think about, right, so we've considered flow throughout the boundary. What can also happen in general, depending on the vector field, is that the inside the rectangle might also produce flow or reduce flow. And there are two main ways that this can occur, physically speaking, right? The flow inside. The next thing we got to consider, and we'll start. I'll circle this because this is going to be a big piece of what we use to get our final equation. We have flow through the boundary is approximated by this summation. And the next thing that we have to consider is flow inside the rectangle. So flow produced inside the rectangle. This is the next thing that we need to consider. And there are two main physical ways that this can happen. Right? The first main way that we'll consider is what's called rarefaction. And what this means is it's compression or an expansion. And a good way of thinking of what compression or rarefaction is if you think of what's called a compression wave, where there's regions of the gas compressing and expanding. Right. So this flow through the boundary should be directly balanced with any rarefaction that's going on inside of this region. So we can directly express that very, very nicely, actually, in the following way. So if we consider how to approximate the total change in mass due to rarefaction per unit time, you'll see that this is approximately equal to negative rate of change of density with respect to time evaluated at the point R multiplied by the volume of the region, delta x, delta y, delta z. So remember, all of these approximations only work when delta x, delta y, and delta z are small enough and the fields are smooth enough to do these types of approximations. But the idea is that this definitely has the correct units. The units of this are mass over time. And this gives us a nice approximation to the change in mass inside the region due to rarefaction. Rarefaction, so that's compression or expansion. And the main idea here is that if the rate of change of density is positive with respect to time inside this region, that means the change in mass is going to be negative. And if the rate of change of density inside the region is negative due to rarefaction or compression, then that means that you'll have a negative value here times a positive value, which means the change in mass due to rarefaction per unit time is going to be positive, because you get negative times negative, which is positive. So this is kind of a very nice justification of why this directly works. And then the other thing is that there are two things that we have to worry about inside the rectangular prism for the mass balance. The other thing that we have to worry about is what's called a distributed source of mass. So if there's something inside this region that's kind of like a pump or producing mass inside the region, that's what we mean by distributed source. And we'll denote this as a function. We'll say that Q of R comma T is exactly the function that gives us the production of mass at the point R and the time T. And this is measured in, it's per unit volume per unit time. And the change in mass shouldn't be surprising that the change in mass due to this distributed source per unit time is approximately equal to this function Q at the point R multiplied by delta x, delta y, delta z. And this is for the exact same region, because this Q is a rate of mass production per unit volume per unit time. So if we have that the change in mass due to source per unit time, or sink per unit time for that matter, if Q is negative, is going to be just the value of this production of mass per unit volume per unit time multiplied by the volume delta x, delta y, delta z. And this is a valid approximation as long as the delta x, delta y, and delta z are small enough. So it's at this point now, right, where we kind of combine everything that we've done, and we're at the final step that we need. So we need to take the three approximations that we've just discussed. So that's rarefaction and distributed source of mass for flow of mass inside the rectangular prism, and also then connect these with the total net change in mass per unit time across the boundary. And this is done as follows. This is, in this example, used to express the conservation of mass. And it's also sometimes called, a mass balance. And what we need when we're doing this mass balance is to say the following. We need to essentially express that the total flow of mass, or net flow of mass, into and out of this region, this rectangle, this rectangular prism, has to be directly equal to the total amount of rarefaction and mass production / sinking inside the region itself. Right, so this is what gives us the so-called mass balance here. And sure enough, if we write this out, what this says is that the x partial derivative of density times velocity v1, or this is at that back face, y plus delta y over 2, plus the y partial derivative, other way around, this should be x plus delta x over 2, the y partial derivative of rho times v2 at the back face, y plus delta y over 2, plus the z partial derivative of rho times v3 at z plus z over 2, all of this times delta x, delta y, delta z. This should be exactly equal to, this gives us the net flow of mass through the boundary. This should be exactly equal to negative d rho dt, the partial derivative of density with respect to time, plus the source rate. All of this is evaluated at the point r, and this will be multiplied by delta x, delta y, delta z. And what we have is that, first off, the volume, delta x, delta y, delta z, ends up dividing out. So we have a nice simplification here. And not only that, but this should be delta, the delta right here, and a delta right here. What we're really considering, right, this is all an approximation until we take the limit as delta x, delta y, delta z go to 0. Because that's going to make essentially give us what we're looking at, which is all of these expressions are approximations, right, and they become equalities when delta x, delta y, and delta z go to 0, or this cube shrinks down to the point, just the point itself r. And so as we do that, right, or as delta x, delta y, and delta z tend to 0, what we get is the following equation that has to be satisfied. And this is something that has to be satisfied at the point R. But you'll notice that there's nothing special about this point R, and specifically, if we go back to our plot of the vector field itself, so if we kind of go back and we open up that plot, we can do it for either of the two examples. This point R that we're kind of talking about could really be any point inside the vector field. Right, so it's this power that we essentially have, that this equation has to be valid at every single point in the vector field. And this is why this is so important, because what we've just done is essentially derive what's called the continuity equation. And this is an example of the three-dimensional continuity equation, or the three-dimensional equation that expresses conservation of a given quantity, conservation of the quantity rho, in this case, the mass density function. Continuity equation in 3D, it expresses conservation of the quantity rho. In our example, this is the mass density in 3D, right? So through a three-dimensional domain, and this is a very, very, very important equation. But the reason that I chose to derive this equation specifically is because, right, this gives us an exact way forward in motivation for deriving what's called the divergence of a vector field. Right, the left-hand side of the continuity equation. And I should reference that this is the continuity equation in Cartesian coordinates. So x, y, and z coordinates. Right, but the left-hand side of this equation I'll call this equation star, is actually a very special operation called the divergence of the vector field F, where the vector field F is the vector field with components rho v1, rho v2, or rho v3, which is the same thing as rho times v1, or rho times v. But just could as easily be, call it vector field PQR, where P, Q, and R are the function, these functions, rho v1, rho v2, rho v3. So this is why I'm using the continuity equation to essentially motivate the divergence. So the divergence of a vector field F, a general vector field PQR, is defined as follows. We say that it's div of F, and we'll use our underline notation. In Cartesian coordinates, the partial derivative of P with respect to X plus the partial derivative of Q with respect to Y plus the partial derivative of R with respect to Z. By the way, we can kind of write this in a clever way by remembering that with the dot product, we can think of this in some sense as a dot product of a special operator called the del operator with the vector F. Now, this is not a normal dot product, because this del is not an actual operator. Recall that the gradient of a scalar field phi is a row vector of partial derivatives, d phi dx, d phi dy, d phi dz. So we can consider the operator del is defined by x partial derivative in the first component, the y partial derivative in the second component, and the z partial derivative in the third component. We can also write this as 1, 0, 0 times the partial derivative with respect to x plus 0, 1, 0 times the partial derivative with respect to y plus 0, 0, 1 times the partial derivative with respect to z, which is the same thing as I hat transpose ddx plus j hat transpose ddy plus k hat transpose ddz. And this is sometimes the most convenient way of changing to a new coordinate system, changing bases, and something we have to be very careful about if we kind of try to view what the divergence looks like in a new coordinate system. So we'll get into that a little bit later. But what's nice about this expression right here, the divergence expression right here, is that the continuity equation, or the balance of mass, actually ends up looking like this. It's that the divergence of the vector field rho times v is equal to q minus partial rho partial t, d rho dt. And remember, the divergence of rho v is the same thing as this del dot product with rho v. This is one way of rewriting this continuity equation. An equivalent way of rewriting it is writing it as d rho dt. If we add d rho dt to both sides, it's d rho dt plus the divergence of rho v, rho times v, is equal to q. And this is another common way of looking at and reading the continuity equation. This way is nice for a number of different reasons. One of the main reasons is that we can actually look at this in a slightly different manner, right? One of the properties of the divergence that's really nice, and I recommend you going through and showing, is that as long as the vector field v and the scalar field rho are smooth enough, the divergence obeys a sort of product rule. So I'm not going to go over all of the properties in detail, but one nice property that we have here is that the divergence of rho v, and proving this isn't too bad. This is as long as rho and v are smooth enough functions. What that means is that enough of the derivatives are continuous. Then we have that the divergence of rho times v. Well, if you look at this component wise, this ends up being in Cartesian coordinates the x partial derivative of rho times v1 plus the y partial derivative of rho times v2 plus the z partial derivative of rho times v3. And each one of these combinations is a function times a function, so the normal product rule is obeyed. And I'm going to let you fill in the details here. It's a very good exercise. But what ends up happening is that this actually becomes the gradient of rho dot product with v plus rho times the divergence of v. And this is a sort of product rule that is obeyed by the divergence. And what's nice about this and kind of useful about this is that this can be rewritten to be here this is the rate of change of density with respect to time plus now this will be the gradient of rho dot product with v plus rho times the divergence of v is equal to q, is the same as this expression right here. And we can simplify this a little bit more, right? This expression right here for this quantity the first two terms in this summation is actually what's known as the material derivative. Because if you're following a point particle traveling along some path through this vector field, so you have some path line, some curve, right, which is a path line, where the velocity of the particle is along this field. Let's say the velocity of the particle, this curve is given by r of t, the velocity of the particle, then r prime of t, we'll say, is equal to v, the velocity vector field of this fluid flow, and you want to figure out what the derivative, the total derivative of the density function is along this curve, or the total derivative d dt of the density function along r of t, and where density function is also a function, explicit function of time. By the multivariable chain rule, this is exactly equal to the partial derivative of rho with respect to t plus the sum of all the partial derivatives of rho with respect to x, y, and z times the velocity component in each one of those directions, which simplifies to this as we've shown before. This is why we sometimes call this entire thing the material derivative, and we just call it d rho dt, where it's normal to use lowercase d's for the derivative, but the material derivative has a slightly different notation here across many math and engineering texts. So in fluid dynamics, this is then plus rho times the divergence of v, that's still equal to q. So this is an alternative way of writing down the continuity equation in terms of the material derivative, or in terms of how this expression changes along path lines of individual particles. So we can give a good kind of summary of exactly what it is the divergence of a given vector field means. And it's kind of an intuitive summary here. And what we'll do is we'll consider the divergence in 2D, not in 3D, but this interpretation also holds in 3D as well. This is the sort of physical interpretation. So the idea here is that the following, it's first off, in 2D, this interpretation is in 2D, but like I said, it also applies in 3D. In 2D, the divergence of some vector field, we'll call it capital V, where we have V1 and V2, V1 and V2, V1 and V2. Divergence of the vector field V is the sum of the x partial derivative in Cartesian coordinates of V1 plus the y partial derivative of V2. And at a given point, say R, if the x partial derivative at R is positive and the y partial derivative at R is positive, then that's going to mean the divergence is positive. And in general, we can kind of think of R as a source point. Right? In general, if you put a box around R, in this case in 2D, but this also holds in 3D, when the divergence is positive, that means in general there is more more vectors flowing out of the point at R from this vector field than flowing in. And so R is, in some sense, it's kind of like a source. And to the direct contrary of that, right, if both of these partial derivatives are negative, then we can think of the point R as being a sort of sink, right? Because this is saying that R, in general, if you draw a small box around R, the point R, when the divergence is negative, there's more vectors going into the box than coming out of the box. So that's essentially what this is saying. And this even applies if these derivatives are mixed. So if, say, v1 is positive and v1 is negative, well, the sum of those two values is either going to be positive or negative, right, depending on which one's a bigger value or has a bigger magnitude. And this is still going to tell you exactly the same interpretation that I was giving before. If this is positive, if the divergence is positive, then R is kind of like a source of vectors, because there's more vectors going away from R than going into the box around R. If the divergence is negative, then there's more vectors going into the box than coming out of the box. And then the last case, if the divergence is equal to 0 at a point, then that means the total amount of vectors going into any small box around the point is exactly equal to the total amount of vectors going out of any box around that point. So there's no source or sink. The point is neither a source nor a sink. And this is actually, it brings us to a very interesting, definition of what's called an incompressible vector field. So we define an incompressible and this is typically reserved for fluid flow fields, but it could apply to any vector field. Vector field is sometimes called a solenoidal vector field as well as a vector field or let's just say if the divergence is equal to 0. Within some region. Omega. And really we'll be very, very clear here. This is only within the region omega that it's said to be solenoidal or incompressible. So we say that the vector field F is solenoidal or incompressible within some region omega if the divergence of the vector field is equal to 0. Within the region omega. And I'll be specific here, we'll say the divergence of F, of the vector field F. because and this makes a lot of sense in some ways, in a lot of ways. So we'll include solenoidal as the main definition here, but incompressible is also a good way of thinking of this. So the idea here is that the vector field F is solenoidal within omega if the divergence of F is equal to 0 within some region omega. This is, incompressible is a nice word here because the idea is that when the divergence is equal to 0, that at any point, that means that that point is neither a source nor a sink. So what that's telling you is the following. It's if you have some region in three-dimensional space, this region omega here, and this is a 3D region in general. If the divergence is equal to 0 of the vector field at every single point inside this region, that's like saying there's no sources or sinks at any single point inside this region, right? Which is why we can say that this is the same thing as incompressibility in some sense, and this is directly related to the idea of incompressibility in fluid dynamics, right? When we talk about incompressible fluids, by the way, if a fluid velocity field is incompressible, then the continuity equation does simplify a little bit as long as the solution is valid and the functions are smooth enough. It simplifies to just the material derivative is equal to the source function, because this divergence is equal to 0 for incompressible fluids. So this gives us this definition right here. And this should wrap up our understanding of the divergence of a vector field.